All right, everybody, shall we get going? Thanks for coming along to my talk. My name is Noel Welsh, and I am a consultant at a company called Underscore. But I'm not here to talk about that. I'm here to talk about some weighty philosophical topics. So let's start with a bit of audience participation here on this topic. Is Python a good language? So one of the ways that we can settle things is with utilitarianism, which is you go for the greatest good. So let's have a vote. And we use utilitarianism to decide in the audience, is Python a good language? So put your hand up if you think it is a good language. I will vote on the side of good as well. And put your hand up if you think it's a bad language. All right, we have a few hands going up. So the audience says that Python is a good language. And this question was what motivated this talk initially. Somebody asking me, isn't Python a good language? And I thought, well, you know, what is good, and can we really give a sort of definition of good outside of a context, particularly for programming languages, and particularly for when the programming language which are in different kind of paradigms, object-oriented and functional programming. So this talk, I want to talk about the difference between object-oriented and functional programming, what it means to be a sort of object-oriented programmer, what it means to be a functional programmer, and hopefully, if you are new to Scala, maybe give you some ideas on how you can more easily adopt the functional programming mindset. And if you're a more experienced Scala developer, then it's likely that you're training people at some point in time. So maybe you can use these ideas to help train people. So yeah, we're looking at OO versus FP, what it sort of means to think in these different ways, and what it means to be a functional programmer. But before I get into that, I want to discuss some other ideas to give a bit of context. So let's talk about some wild ideas from the 60s. Now, let's say we have another look at the audience. I'm going to guess that nobody here remembers the 60s. But if you think of the 60s, you probably think of Woodstock or maybe the Beatles or things like that. But there's some pretty wild ideas coming out of Paris in the 60s. I want to discuss some of them, and I suspect they're probably not familiar. So let's talk about, firstly, taxonomy of angels. I don't know if you've ever considered this. Are angels all one species, or are angels separate species? Well, it's been argued that angels are separate species because angels do not have matter, and you cannot distinguish things that you cannot distinguish individuals if they do not have matter, if they're all of the same species, so angels must be of different species. Interesting idea? What about the nature of intellect? Well, you can use the same argument, because all educated people know intellect has no material substance, and therefore we cannot distinguish between individual intellects, so all humans share the same intellect. So that's kind of an interesting thing. It kind of makes the whole talk pointless, right? If we all share the same intellect, then I don't need to tell you anything, so you know it already. Oh well. How about this one on the immovability of the universe? God cannot move the universe in a straight line, because to do so would be to cause a vacuum to exist where the universe was, and as we all know, vacuum is impossible. Reasonable idea? I should probably at this point point out, when I talk about the 60s, I'm talking about the 1260s. And the ideas here are given to some people called the Latin Averroists, and Thomas Aquinas, you may have heard of. And they were considered pretty far out at the time. And there's one thing you can expect if you've got far out ideas in the Middle Ages, and that, of course, is the Inquisition. So in 1270, the Bishop of Paris had this condemnation of the ideas I've given previously, and here's some more of the ideas that were condemned. You weren't allowed to think in 1270. The soul separated from the body by death cannot suffer from bodily fire. God cannot grant immortality and incorruption to a mortal and corruptible thing. God does not know singulars, individuals, creatures. God does not know things other than himself. And many more. If you really want a bit of insight into how strange things were in the Middle Ages, looking at these or the condemnation of 1277 is interesting. And what I find interesting about these ideas is they seem very strange to us, but they seem strange in a very strange way. It's not like somebody saying dynamic typing is the best way of programming. that's something I can imagine having a reasonable debate about, something where we have some common ground. And even though I don't believe dynamic typing is the best way to program, it's something I think I could discuss. Whereas if somebody asked me to discuss the taxonomy of angels, angels are one species or many species, I don't know where to start. I mean, what is an angel? What are the rules for manipulating an angel? I mean, I could sort of vaguely remember D&D 3rd edition, but I don't think that's really going to be helping me in this context. It's something where I don't even have a sort of intellectual basis to start thinking about this from. So to try to sort of pin down what's going on here, I think we need to turn to some wild ideas from the 60s. But here I am talking about 1962 in particular, and this book, The Structure of Scientific Revolutions, by a guy called Thomas Kuhn. And this was a sort of landmark publication in the philosophy of science. And up until this time, people had seen science as a very sort of rational process, and he introduced an element of the human to it. And in his model, science was divided into two stages, mainly. What was normal science? When you're running around in your lab coat, having a good time, doing experiments, writing papers, getting results, everything's working well. You're working within some existing theory. So your experiments tend to accord with that theory. They make sense when you interpret them under that theory. But every once in a while, things go wrong, and you have to storm the barricades, and you have a scientific revolution. And this is when the old theory just can't explain the results you're seeing sufficiently, and you have to come up with some new ideas, a whole new way of thinking about the world that's going to explain these results. So examples are the Copernican revolution, where we went from the Ptolemaic astronomy, everything revolves around the sun. You've got to understand, it wasn't just everything revolves around the sun with the laws of motion as we understand them. We had things like vacuum cannot exist and things like this. So I sort of worked out theory of the universe, but one that didn't really do a very good job of explaining the observations of the planets we could see, to the model that we have today, where things revolve around the sun, so rather than revolving around the Earth. I think I might have said that the wrong way around. More recently, we had things like relativity and quantum physics, which gave us a completely new way of looking at the world, where things are much less certain than we believed in the kind of Newtonian mechanics. And we have these strange effects when you move very fast, you get time dilation, all that kind of stuff. So this is what a revolution is. And this book, Structure of Scientific Revolutions, actually coined the term paradigm shift. So the next time you see a manager telling you what we need is a complete paradigm shift, you've got a philosopher in your ranks. Isn't that cool? Something to use. So this idea of going from one sort of way of looking at the world to another way of looking at the world is the paradigm shift. And the other thing that we have is when we go from one paradigm to another, there's this technical term there, incommensurate, which basically means that from one paradigm you have just this way of looking at the world that you can't really square up with the way of looking at the world from the other paradigm. And so when people from one paradigm talk to people in another paradigm, they just don't make sense to each other. And I think that's what we sort of saw with those medieval philosophies. To us, they're not even sensible questions to ask, let alone looking at the kind of answers they've got, the arguments. Just why would you even be talking about this? Why would you even be discussing whether God can move the universe in a straight line? It just doesn't make sense. And that's what I mean by incommensurate. So we can take these ideas and we can look at object-oriented and functional programming in this lens. That's what I want to do now. Look at these structural programming revolutions. So to my mind, there have been three main revolutions in the history of programming. The first one was structured programming, which started in the mid-50s. So up until this time, people were written in pure assembler if they had assembly. And you had sort of any ad hoc control flow. I think most people probably, if you did a computer science degree, you would have learned a bit about this. In 1968, we had this publication, Go-To Statement Considered Harmful, which is kind of like set the intellectual program, if you like, of structured programming. And the idea was to provide some structure to the control flow. That's where we get our for loops and while loops. I think we can say by the 80s and the mid-80s, this idea of structured programming dominated the industry. So I think C was probably the most commonly used language then, Turbo Pascal, this type of things. So that's structured programming. Next, we had object-oriented programming. Started sometime in the 60s, I think 67, Stimulus 67 was the first OO language. Hit maybe its sort of high watermark is Smalltalk 83, and then by the late 90s, certainly, I would say it dominated the industry, C++ and Java. That was OO. And then functional programming, you might recognize the face there behind the slide. You could say it maybe started in the 50s with Lisp, but I would say it started more in the mid-70s with Scheme over here in the US and ML over in Edinburgh, really bringing forward the ideas that we have in modern functional programming. What's quite interesting here is if you look at this timeline, you see things that are very recent. So Haskell, 1990, monads, only 1995. That's really quite recent. Applicative functors, something that you may or may not use quite a bit, 2007, and we could go down this list. Things like the free monad only really became popularized or widely known in the programming community within the last 5 years or so. Data type a la carte is one of the publications there. I think that was 2010. So functional programming is really quite new. The foundations are old, but the fully developed theory of functional programming is quite new and is ongoing right now. And I'd say this is the revolution that is sweeping the industry right now. So we are going through a change in the industry from object-oriented programming to functional programming. And if you look around the industry, this is everywhere. So obviously we have Scala on the JVM, and of course Scala runs on JavaScript and will no doubt be running on native code as well, as we'll find out later today. But other platforms, iOS, we've got Swift, very new, Rust for systems programming. In the JavaScript world, other than Scala, we have lots of really interesting stuff going on. Elm and PureScript, Flow, which is a type checker, and React coming out of Facebook using functional ideas. And distributed systems, of course, Scala lives in there as well, but languages like Pony are doing really interesting things in bringing functional programming ideas, type systems to distributed systems. So really interesting stuff there, I think. So if you accept this model of the paradigm shift and that the functional programming revolution is sort of the paradigm shift happening in our industry, then the obvious thing to ask is, what is the functional programming paradigm, and how does an object-oriented programmer make the change? So I want to talk about that now. What does it mean to be a functional programmer? In particular, when I think of the paradigm, you can think of the basis of your thinking about programs. So how would you describe programs, or how do you think about programs working in terms of sort of a program executing or not executing, depending how you view them? And then what is your sort of aesthetic? What do you see as being good code? How do you separate good code from bad code? How do you decide how you should use the language constructs to construct code? So to give a bit of context, in fact, let's do a bit of audience participation. I've seen most people have experience with OO. So who would like to tell me how I think an OO programmer might think about programs? What do you think the components of programs are? Anyone? It's not a trick question. You can't get the answer wrong. Nouns. Sorry? Nouns, yeah. Okay, so nouns are objects. Yeah, indeed. How do yeah.
And also, but keeping the operations that work on that data and that object close to that object.
Right. So an object is sort of encapsulating data and the methods that work on that data. And that is kind of like an object is a noun. Yep, definitely agree with that. Anything else? How do objects communicate? No? Wow, tough audience. Yeah, messages. So message passing. I'd agree. Anything else? You're all Scala programmers already. You're all completing the functional programming paradigm, and what I'm talking about is absolute nonsense. It doesn't make any sense.
There's things like the Liskov substitution principle. I mean, there's all that stuff.
Yeah. Yeah, definitely. Okay, great. So we've got some answers here. So I would say objects, message passing, and polymorphism would maybe be the fundamentals of object-oriented programming. The problem with this stuff is not very clearly defined. You sort of become like biblical scholars of the 1260s arguing about Alan Kay's writing, what the true meaning of OO is. But yeah, you mentioned solid principles, single responsibility principle I have here. So these are some of the things that object-oriented programmers use to think about code and to guide themselves to writing good code. Important points here is this is quite an informal model. Like I said earlier, this kind of discussion of Alan Kay's writing is how do you interpret his writing to determine the true OO nature. So it's quite informal. It's also quite anthropomorphic, which I think is just interesting to point out, this idea of objects being kind of active things talking to each other via message passing. And it's also, I find, quite a dynamic model. So one of the things about polymorphism is that many different objects can accept the same message, and whatever they do with that message is up to them. So the meaning of your program, what your program does, is really only truly known at runtime. And that I see as fairly important in OA thinking. All right, anyone disagree with that or sort of like to have extra points? No, okay, so you all agree, fantastic. So let's move on to functional programming then. How do functional programs think about data? I would say the core thing for an FP person is you look at a program as a transformation of data, it's a sequence of transformations. And if I had to boil down into two ideas, what are the core things that functional programmers value? I would say simplicity and static reasoning. And these require more explanation. So simplicity is one of these kind of words that programmers use to hit other programmers with. My code is simple. Yours is convoluted. And often people, what they mean by simplicity is, my code uses things I understand, your code doesn't. So we need to be clear on simplicity. And many languages will claim to be simple. I think Python will claim to be a simple language. Go, in particular, claims to be a simple language. That's one of the main sort of points they make in their kind of philosophy. And so if Go is a very unfunctional language, how is its simplicity different to the kind of simplicity I'm talking about? Maybe the simplicity of Scala or Haskell. So what I mean by simplicity is it's as few concepts as possible at all scales. And it's this at all scales which is the important bit. So having as few possible concepts at the low level and at the high level. And let's see some implications of that. So one implication at the low level, you have control structures. In your typical OO language, sort of inspired by structured programming, you have for loops and while loops and do loops, and you have recursion. And in functional programming language, what you say is, let's get rid of most of those and just have recursion. Because recursion does everything you can do with those looping constructs and more, so why have these extra things when you don't need them? You can just have tail recursive loops and everyone's happy. Then the high level, we should look at abstraction. So if we have these things, a list of A, option A, future A, be familiar, Scala programmers. In your typical object-oriented language, what can you say about these things together? And I think the answer is nothing. I'm sure you all looked at that and thought, well, that's a monad. But OO languages don't typically express the concept of monads, or they don't have the language features like high-kinded types needed to make this abstraction. And abstraction makes things simple because it makes different things the same. So you can have one mental model, like the monad, and you can think about all these different things using that one mental model. That also can explain why things like monads are kind of difficult to understand because they are so abstract. They get their power from being abstract because you can explain many different things in this one way. But we all have difficulty reasoning about abstract concepts. So it can be difficult to learn how to use that abstraction. As I think Rich Kiki said, simple and easy are not the same thing. Another way we can look at aspects of the kind of functional programming paradigm is how we model evaluation of a program. So I earlier said that the OO view of a program is a very dynamic process. Whatever happens at runtime is what happens because you've got polymorphisms and so on, or objects sending each other methods. Whereas in the functional programming world, we have this model of substitution that we lean on heavily. So here is an example program, 1 + 1. And can anyone tell me what this evaluates to? It's not a trick question, again. Come on. OK, thank you. I was really beginning to worry about the quality of the US education system. So that evaluates to 2. Right. And then if we have this program here, this complicated one, what we see is it's got 1 plus 1, which we saw earlier, was 2, and 1 plus 1, which we said earlier, was 2. And what substitution says is wherever you see an expression, you can substitute in the value. So we can say, 1 plus 1, I know what that is, that's 2, and that one's also 2, so we can get 2 plus 2. And then can you tell me what 2 plus 2 is? Excellent, 4, okay. And away we go. So hopefully this seemed really kind of silly and stupid to you, and that's kind of the point, is that this is really, really easy. It's simple, it's just one concept. So my definition of simplicity is this one concept. It's very easy to work with. We learned how to do this in probably primary school, maybe high school. Yeah, I don't know, you might call the schools different things here. Another point is that it's compositional. So when we looked at the meaning of 1 plus 1, plus 1 plus 1, we could look at the meaning of these two things separately, and we knew that this part of the expression, say, is not going to affect the meaning of this part, so we can reason about them individually, and then the meaning of the two individual parts just comes from combining those two bits together. So that's compositionality for you, where you can think about things in isolation and then combine them. So substitution is a very nice thing, and how is that expressed in our language? Well, one way is at the low level, we have sort of expression-oriented languages. So in Java, if you're doing some kind of comparison, you might write something like this, because if is not an expression, doesn't return a value, you'd have some variable, and you would just have to assign the variable this value of this comparison. Of course, in Scala, you can write like this instead. Val x equals if. That's a bit of a mental leap for someone used to if being a statement, not an expression, to make. But it does give you just this one rule. This is how you can just use substitution here to think about this. You can't think about this just with substitution because you have state, and state breaks substitution. Okay, so that's kind of how things work at a low level with trying to maintain substitution. At a high level, something we often see is separating describing and running a computation. That sounds really fancy, but it's a reasonably simple idea. And here's a small example using kind of IO monad pseudocode. Let me explain what's going on here. Hopefully you can read this just as code. Here we're opening a file. We're reading all the lines from the file. We're printing them all out to the console, I guess, and then we're closing the file and returning the number of lines that were in the file. What's important about this code is nothing actually happens. This code doesn't do anything until we call run. So here we have an IO int, a program that when we run it will generate an int and do some IO. And here we run the program, and we get back an integer. And the important thing about this is that until we run things, until we actually do this running bit, we can use substitution in here. So maintaining substitution is what motivates techniques like monads, or one of the motivations for techniques like monads. So it allows us to maintain substitution in our programs. And we can do this kind of high-level stuff. Right. Another way that we see differences between O and FP is in the use of types. So in a language like Java, types are really, they feel like busy work. You're just doing them to get the compiler to shut the hell up. And the trade-off is you get the compiler to shut up, you get fast code. And there's quite a sort of intellectual movement in OO world away from static typing to the dynamic typing, Smalltalk dynamic types, Ruby and Python, and so on. But in functional programming, we have a different view, which is that types are integral to helping us to understand and to write our programs. So let me give you just the quick examples of that. What does this method do? Without seeing the body, can anybody, not Raoul, tell me what the method is going to do? Sorry? Yeah, returns in. And why is that the case? Are you going to tell me? No? Okay.
Unless you expose erasure, that's the only thing you can do there.
Right. Okay, yeah. So, yeah, we have type erasure, which basically means that this generic type is an abstraction boundary. You've said here that there is some some type A, but when you're inside the body of this code, and let me put up the body, this is the only thing you can write. So it's the identity function, or the identity method, I guess, in Scala. You can't break open this abstraction boundary. You can't look at what this type is at runtime. So there's only one thing you can do. Yeah, you have to return it or throw an exception, diverge. So what this means is that if you're the programmer, you don't have to know what is going on inside this function. When you look at the type as the kind of the user of this method, it doesn't matter what it's called or what it's doing. You can only do one thing. So you can use the type to help you understand the code. The type here is giving you information. This has to be the identity function. Here's another example, a little bit more complicated. We're going to write map on option. This is something we often do as a case study in training, and it's something that the new Scala developers find quite challenging, but I want to show you that really it's just following the types. Types are going to help us write this code. So, because you're a tough audience, I'm not going to ask you to do this. I'm going to lead you through it, the 3 steps. So we'll start with map. This is the signature of map. I've got a typo there. We shouldn't have that A in there. We should write the body. Now, the first thing we know about option, it is an algebraic data type. Being an algebraic data type means we can just apply structural recursion, and this gets us this skeleton straight away. OK, so none and some. Familiar enough. OK, now let's look at this first part here. We have to return something of type option B. The only way we have constructing something of option B is using, of type B is using this function from A to B. We have nothing of type A to give to that function. So there's only one possible thing we can do here. We have to return none. It's the only possible result that will make this code compile, putting none in there. And look at the second case. Well, what can we do here? We could return none, or we have something of type A here. We could put that into this function, get back something of type B, and wrap that up in a sum, getting sum f of A. So we had 2 choices there. So we had to do a minuscule amount of thinking to distinguish the correct option from the incorrect one. But largely the types are guiding us towards the solution. There are only 2 possible paths we could have gone down that the type system would let us go down, and we had to choose the right one. So this is an example of how types guide you to the implementation of code. If you get the structure of the types correct, then the code in often cases just follows automatically. And taking that to its ultimate conclusion is doing stuff like you do Shapeless, type-driven boilerplate generation. So an example is generating JSON serialization just from the structure of your types, something you would do in dynamic languages. Typically with reflection, you can do purely at compile time with Shapeless, and you get the performance advantages and the safety guarantees of doing this stuff in a typed manner. So that's really powerful stuff. So a quick summary of what we've seen. We've seen simplicity and static reasoning, this idea about understanding your code before it's run, I think are the main things that a functional programmer values about code. So very heavily into this idea of understanding our code before we run it. And some of the consequences we've seen in this are the substitution model of evaluation, which is very easy to work. It's very simple, which is one rule we can apply to all of our programs. And it helps us to understand our programs before we run them. Composition is very useful for understanding programs again, because you can understand little parts in isolation. So we try to maintain compositional code. And therefore, you don't have to know the whole code base to understand just the bit you're interested in. Types, again, help us, as we've seen, they help us write code. They help us reason about code. And one of the other things here is this precision. So we have these much more precise definitions of concepts than we saw in the OO world. It's much more sort of mathematical feel, which does scare some people. But I think it's ultimately an important part of it. So the next question is then, if you're an OO programmer, like I think most people are, you have a background in OO, how do you cross from OO to FP? Now one theory is that that's just sort of can't. You should just give up and die. But I don't think that's necessarily the truth, luckily. So what I find really interesting is if you look at kind of the intellectual history of OO, particularly the design pattern stuff that was started in 1994, and I think it was pretty active through 2000s. A lot of FP ideas are present in object-oriented design patterns. Are most people familiar with design patterns? Anyone not heard of design patterns? Okay, one person. Okay. Right. So the design patterns in OO were kind of like, they were ways of using OO languages, collections of OO languages features, which said this is a good way of using classes and objects and so on to achieve this one particular goal. Here's how you might do things. Possibly the best known pattern and the one that everyone hates is the singleton, where you only want to have one instance of a class. So you can say in Scala, we don't need singletons because we have objects. More interesting are things like these patterns, chain of responsibility, command, and strategy pattern. I'm not going to go into the details of what they are. I don't even really remember, to be honest. But what is interesting about them is they're all really just variations on first-class functions. So the command pattern is sort of wrapping up in an object a command, if you like. Something's going to do something. That's a function, basically, though it might have some state in it. A strategy is kind of a way of doing things. Again, it's wrapping up in an object a function, a verb, if you like. And chain of responsibility is kind of a pipeline of objects passing stuff down a pipeline, and that's function composition there. So they didn't see it at the time, but they were exploring functional programming idioms with these object-oriented patterns. It's important, though, that I do think the paradigm is different. So in my OO days, design patterns were always seen as this kind of little extra garnish you put on top of your program, not something that you necessarily had as your core program. And I think these ideas are much more pervasive in functional programming. And of course, we have a different aesthetic of what we consider to be good code, as discussed earlier. So I think looking at the design patterns, if you have a strong OO background, looking at them and then finding their equivalents in functional programming world will help you to understand how to use a functional programming language effectively, but it won't give you that sort of aesthetic that you need to guide yourself towards what is good code versus bad code. And for that, you need to adopt the paradigm. So conclusions. Let's start with something controversial. Multi-paradigm development doesn't make sense. It's kind of like, by definition, if you accept the definition of Thomas Kuhn, then multi-paradigm development does not make sense. I don't think it makes sense either. I don't think you can simultaneously maintain a kind of OO aesthetic and a functional programming aesthetic at the same time, because I think they are in contradiction. I don't think you can do both. Ask me after the talk about this. So hopefully there'll be some questions from that. I do believe, though, if you have a strong OO background, you can look at these OO patterns and you'll find equivalent in FP, and that can help you to understand how to use a functional programming language effectively. But I do think you need to adopt that paradigm as well. And I hope that I have shown that the FP paradigm, is not really so difficult, but it does take time to internalize. There's only so quickly you can learn things. It will take, the journey will take some time. So that's all I have to say. Actually, one more thing. The History of Philosophy podcast, you should go listen to if you don't listen to it already. It's really fun, and that's where I learned about the Latin Averroists and all this kind of stuff. That's all I've got to say. Thank you for your attention and for answering my inane questions. And if you have any questions now, I'll be very happy to take them. It's only fair. Okay, the gentleman at the back there.
What do you think?
Right. So the question is, what do I see as the sort of paradigm beyond functional programming? This is a really good question, and it's a really interesting one. And I think one answer is, I don't know if you can see the other paradigm from within one paradigm, or that's kind of a weaseling out of it. Or you might say, well, we need to run into the problems of functional programming first before we can really start developing the next paradigm, in the way that you have to sort of run into the problems of Newtonian mechanics before relativity was motivated. And we're not at that stage yet. Again, that's just sort of evading the question, I think. So I would say, I think that in the future we might have things like dependent typing, which you might see as an evolution of functional programming, or you might see as something different. I do think that functional programming, because it's based on a much more rigorous theory, I think this it's kind of mathematical theory, it is likely to last longer, and it's likely to have maybe be more correct or have more influence than the things that came beforehand, in the way that you can see relativity as it doesn't completely, it just extends really Newtonian mechanics rather than sort of replacing it. We might see the same thing with future paradigms, extending this foundation of functional programming rather than replacing it. Is that a reasonable answer? Okay. At the front. Right. Okay, so the question was, you've read that you should sort of 80% of your code functional, 20% a bit of mutation and so on, but I said that OO and functional programming are not commensurate. Let's use our fancy terms. Functional programming. The other thing I should have put in the functional programming, we love fancy words. Absolutely love them. Algebraic data type, structural recursion, all these great names. Fantastic stuff. So, okay. I think that's a really interesting question, and it's something I didn't really get into because it really made the talk too long. One thing about functional programming is it's not state itself that's the problem, it's just controlling state. So this idea of separating a program from describing the program and then running it. When you run it, you can have all sorts of side effects. That's what you're meant to do. You're meant to have side effects in state, and that's fine. You just have this clear separation. So you go, here's a program, this part of the program you can reason about with substitution. Everything's happy. Then you go and run things, and then you can just do whatever you want. Side effects, open files, print things, do graphics, that's fine. And that's where you get all your kind of gnarly techniques. There's another thing. So I talked about how if you sort of follow OO design patterns, you end up in functional programming. Well, there is a convergence happening in some directions. So we had to talk about the sort of free monad, and that was yesterday. There's a similar idea called a finally tagless interpreter. So I told you functional programmers love fancy words. And if you look at this finally tagless stuff, and you look at something coming out of the OO world called object algebras, slightly less fancy term, they actually are really doing the same thing. They have a slightly different basis they're coming from. The sort of lack of high kind of types in the OO world, and makes the object algebra stuff a little bit more painful. But it's essentially reaching for the same spot, and they're almost equivalent. So I do think that there's some convergence going on here, and if you sort of go down the rabbit hole far enough in functional programming, you pop out in OO, and if you go down the rabbit hole in OO far enough, you sort of pop out in functional programming land. So I think there's more synthesis there than I perhaps led on in this talk. And again, you can see objects as being sort of dual to functional programming ideas, and that's getting into more kind of nerdy functional programmer speak. But I think there is a kind of a synthesis there, and that's something I want to explore in my own talk. Right. Okay. So the question, I'll repeat it for people who can hear at the back and for the video, is the responsibility of the Scala community to develop Scala as an object-oriented functional hybrid, or to treat the OO part as your way into Scala, and then we want to go functional. Yeah, I think certainly there's divisions in the Scala community. We don't all agree on how we should write code, and different people write code in different ways. And I should have perhaps mentioned, within the Scala community, you might even say there's a third paradigm, which is the actor paradigm, which is kind of OO-ish in this message passing, but it's also has its own differences. And this is why many people, I don't particularly like akka because I don't like the fact it's in a different paradigm, doesn't maintain my values. But yeah, getting back to your question. Now, one thing I think is interesting about what Martin said in his keynote was that Scala is a functional modular hybrid, not a functional OO hybrid. And at the risk of being a bit of a biblical scholar trying to read the tea leaves, I have found that I like using objects as modules, as namespaces. Classes as namespaces works very well for me. But things like OO patterns of inheritance and these kind of deep inheritance graphs and encapsulating state and that kind of stuff doesn't work. So I do think there is I think we can use these OO features of objects and so on in a way that it works within the functional programming paradigm. But there's sort of OO language features, but we're not using them in an OO way. We're not creating deep graphs of inheritance and using state and stuff like that. So I think that's one way of kind of uniting the two. I do think, though, that the OO patterns, if you like, the things that people typically use in OO languages, for me, they don't work. I can't understand them. I can't understand code written with them. They don't give me the kind of flexibility I want. So I do think the OO way thinking, yeah, that's your way into Scala, and you should move out of it towards an FP way. Of course, I'm in the FP paradigm, I would say that. But I do think that the sort of language features or objects and so on have value. Not differing degrees of value, but they certainly have value. All right. So, any more questions? Anyone? No. Well done. Okay, well, thank you very much for listening.